Hello, in this video I am going to demonstrate to you how to classify compounds in terms of aromaticity. So we are going to use the terms aromatic, anti-aromatic, or non-aromatic. There are a set of rules that we have to follow in order to classify a compound as being either aromatic, anti-aromatic, or non-aromatic. The first set of rules here that we can employ is called the Haeckel's rules. According to Haeckel's rules, a compound must meet the following three conditions. Number one, it must have odd number of electron pairs. That is the pi electrons. The total number must be odd for the compound to be aromatic. Number two, it must be cyclic. Number three, it must be planar to allow for delocalization of electrons. Okay? If we want to classify a compound as anti-aromatic, according to Haeckel's rules, it needs to have the total number of pi electrons. We need to have the pairs being even numbered. Okay? It needs to be cyclic, it needs to be planar. If a compound does not meet these conditions for being aromatic, and it does not meet these conditions for being anti-aromatic, then it's non-aromatic. For example, if it is not cyclic and it is not planar, then obviously it's non-aromatic. Let us see how we can employ that in an example. So here we have one double bond. So every double bond means that we are counting 2 pi electrons because each carbon constitutes 1 pi electron. So one electron pair, another electron pair. So 2 electron pairs, that is going to be even. So this is anti-aromatic. Here we have 1 electron pair, second, third. So 3 electron pairs, that is aromatic. Here we have 1 aromatic. Here we have a formal charge of -1. That means there is a lone pair of electron on that carbon. So we have 1, 2. So that is going to be anti-aromatic. We do not have any pi electrons on this compound, so it's going to be non-aromatic. So we can just continue doing that. 1, 2, 3, 4, 5, 6, 7, 8. That is even number, so anti-aromatic. And I want you to practice these other ones. Another rule that we could use is called the frost circles. So here we have to draw the frost circle using these steps. And I want you to follow those steps and make sure you can draw frost circles properly. And then we can use them to predict the molecular orbital energies. And then once we predict the molecular orbital energy, we fill them from the lowest to the highest. Okay? One key thing you need to consider while drawing the frost circles is make sure the bonding molecular orbitals, the number must be odd. So we need to have odd numbers. So here we have 1, 3, 3, 3. You can see then 5, none of them is even numbered. So make sure the bonding molecular orbitals are odd numbered. Okay? Let us see how we can practice that. Assuming that we want to find out if cyclobutadiene is aromatic or anti-aromatic or non-aromatic, we can use frost circles. According to the frost circles rule, you draw a circle, then if it is 4-membered ring, you make sure each corner touches the vertex, and then the one that is at the lowest is going to be a molecular orbital. And we said if you have many rings so that you can be able to have a good number of them being in the molecular orbital, then you must make sure they are odd. Okay? So, once we have the molecular orbitals, then we can fill them with the electrons. So what you do is, there's a total of 4 electrons, because we have 2 electron pairs, which means there are 4 electrons. So 1, 2, 3, each molecular orbital can have a total of 2 electrons. Okay, so then we end up having 2 that are not paired. Now, actually, once you draw the Frost circle, you can just transform it into the molecular orbitals with energy levels, where you have the lowest, then these ones are in the non-bonding, so these are degenerate. Because they are degenerate, we have to follow Hand's rule. No pairing until each of them has 1 electron. Then the anti-bonding. So it means that the existence of the unpaired electrons implies that the compound is not aromatic. Okay? So therefore we know this compound is not aromatic, but Frost circles can't really tell us whether it is anti or non-aromatic, but we know that it's not aromatic. So we can employ Frost circle and then Haeckel's rule to help us predict the aromaticity. Let us go to a more challenging example. In an 8-membered ring, which is cyclooctatetraene, we can be able to predict the aromaticity, but let us see whether we can do that with high precision. Okay? So we can use Haeckel's rules, and then we're going to have 1, 2, 3, 4, which implies that it's likely to be anti-aromatic. Okay? Let us use Frost circles. So we're going to draw a circle, and then we make sure that we have the 8 vertices, where we're going to have 3 at the bottom. Now, how do we decide whether we are supposed to have 3 or 5? We need to make sure that we can have the total number of electrons being paired in the molecular orbital first. So because it has a total of 8 electrons, we're going to have 6 going over here. So the molecular orbital is going to have 3 of them being full. And then we're going to have the other ones going to the non-bonding molecular orbital. So this compound, according to this rule, it's not aromatic. Okay? And it turns out that this compound is actually non-planar. If you force it to be planar, then there is a ring strain of about 135 degrees. So therefore, it prefers to be in tub shape. So the tub-shaped compound, in this case, now it's not on the same plane, so there's no way for the electrons to be delocalized around the ring. So this compound is non-aromatic. How can you be able to predict that? You can use a molecular model. If you're not able to access the molecular model, at least you need to know the ones that we have discussed. Okay? Now, when we have fully conjugated compounds, we call them annulenes. So like benzene, we can call it 6-annuline, where 6 refers to the number of carbon atoms, as long as there's full conjugation. This is 14-annuline, 22-annuline. Most annulenes are aromatic, okay? But some are not. For example, we have learned that 4-annuline, which is cyclobutadiene, is anti-aromatic. We have also learned that 8-annuline is actually non-aromatic because it acquires a tub shape. How about 10-annuline? Well, let us find out why is it non-aromatic. If we use Haeckel's rules, we're going to have 1, 2, 3, 4, 5. So we expect it to be aromatic. So then, if we do a molecular model, then you realize that it experiences steric strain from the hydrogens. When you do the molecular models, these hydrogen atoms are actually right in the face of each other. So the molecule does not like that, so therefore they are going to project out of the plane. when they project out of the plane, then now it makes the molecule non-planar. Okay, so due to steric strain, the compound is going to be non-planar. Anytime it's non-planar, it means it cannot be aromatic, it cannot be anti-aromatic. Now let us look at the aromaticity in rings with formal charge. This is a 7-membered ring. If we want it to be aromatic, what kind of charge is it likely to have? If we give it a negative charge, what's going to happen? That means we're going to create 2 lone pairs there. So we're going to have 1, 2, 3, 4. Well, that is even number of electron pairs. So that's going to make it non-aromatic. Well, I mean anti-aromatic. But what about if we give it a positive charge? If we give it a positive charge, then this is what happens. There are no electrons there, so now we have 1, 2, 3. So we have 6 electrons in total, which is 3 electron pairs. So that makes it aromatic. And this compound is actually planar, so therefore it turns out to be aromatic. If we want to fill those electrons, 6 of them, we're going to have 1, 2, 3, 4, 5, 6. So all of them are paired. And we can draw the resonance structure where we can actually push those arrows. That one goes there. And then we're going to, when we do that, we're going to end up with 7 resonance structures. So this compound is stabilized by resonance and also by aromaticity. Okay? If you have a 5-membered ring, what kind of charge do you think will make it aromatic? If you give it a negative charge, then it will be aromatic because we are talking of lone pairs of electrons on that carbon. So then we're going to end up with 6 electrons. So 1, 2, 3, 4, 5, 6. And we can draw 5 resonance structures. Once we give it that negative charge, we can draw 5 resonance structures. Because what we can do is we take these lone pairs and then we move it there, and then we're going to do that continuously and end up with 5 resonance structures. Okay? Now, why is cyclopentadiene more acidic than cycloheptatriene? And I want you to look at this question carefully. Cyclopentadiene has a pK of 16. The one for cycloheptatriene, it has a pKa of 39. Now, let us see what kind of formal charge we are going to get when this compound is deprotonated. So when we have this one deprotonated, we end up with aromatic compound, similar to what we had here. When we deprotonate the cycloheptatriene, we create an anion, which is not aromatic. And we know that aromaticity plays a role in stabilizing the conjugate base. But although we do have 7 resonance structures that we can draw from here, see, we're going to have a negative charge, so we can draw 7 resonance structures from there. We can also draw 5 resonance structures. So in other words, resonance structures alone is not a measure of stability. Aromaticity plays a much bigger role. Okay? So therefore, this is due to aromaticity. So because it wants to be aromatic, it just wants to give out that proton so that it can be aromatic. Let us look at the aromaticity in heterocyclic compounds. When you talk of heterocyclic compounds, we mean that the compound has atoms other than carbon and hydrogen. Okay? So like in pyridine, the carbon is replaced by a nitrogen. So now it's no longer a benzene. And this compound is already aromatic. It has 3 electron pairs. So it does not need these lone pairs to make it aromatic. If there's a way for a compound to achieve aromaticity, they would become aromatic by any means. Okay? If you look at pyrrole, pyrrole has lone pairs of electrons on nitrogen, so it can utilize those lone pairs to make the compound aromatic, similar to furan and thiophene. Okay? If those electrons are to be utilized to make the compound aromatic, that means it has to be planar. Then those electrons must be in the p orbital so that they can be delocalized. Okay? Now, why is pyrrole more acidic than pyridine? Okay, look at pyridine here. The pKa is 5.2. Pyrrole, the pKa is 0.4. That's a big difference, okay? So then, how can we justify the difference that we see here? Now, if we look at the pyridine can participate in a proton transfer, so it's going to act as a base. It does the proton transfer, and after that, it is still aromatic. Okay? Now, pyrrole utilizes these lone pairs to make it aromatic. But if you want it to act as a base, then it is going to pick that proton and then it turns into the conjugate acid. The conjugate acid of pyrrole is non-aromatic. So it does not like that. So what it does is that it's going to make sure that it dumps that proton. It wants to dump it so that it can re-achieve the aromaticity. And that's why it is going to be too acidic. It's looking for anything that would be able to grab that proton from it so it can re-achieve the aromaticity. Thank you for watching and have a good one.